Okay, let's finish up these quarter 4 test study guide questions, starting with number 18. I did finish off 18, right? Yeah. Okay, so how many protons, neutrons, and electrons are in the following isotopes of calcium? So remember, what makes something an isotope? It's that it's the different numbers of neutrons, okay? Different numbers of neutrons, same number of protons, different numbers of neutrons. So what we see here are two ways of showing isotope notation. The number you see here in the top left, or written after the dash, these are two different ways of writing the same thing. That's called the mass number. That's the number of protons plus neutrons, not the atomic number and not the atomic mass. This is the mass number, the sum of the protons and neutrons. All right, so let's go with this one first. So I'll do protons, neutrons, electrons. So we have a calcium with a mass number of 40. Well, what do we know about calcium always? Unquestionably, it's that it has an atomic number of 20, meaning it's 20 protons. That is always true about all forms of calcium, no exceptions. By definition, calcium is 20 protons. Well, since the mass number is 40, if it has 20 protons, it must have 20 neutrons as well. So the calibration is a little off here, 20 neutrons as well. And this particular calcium, for the number of electrons, if it's a neutrally charged atom, then the protons must equal the electrons. And since this one has no charge, it must have an equal number of protons and electrons, so 20. So this one is 20, 20, 20 right down the line. This one here, protons, neutrons, electrons. So calcium 42, well, it's still calcium, so it's still 20 protons. But here we have a mass number of 42. So 42 minus 20 gives us 22 neutrons. And it still has no charge, so it still has 20 electrons. For the last one, protons, neutrons, electrons. All right, it's still calcium, right? What's the difference here? The 2 plus, that's the charge. So, but it's still calcium, so it's still 20 protons. For neutrons, we see a mass number of 20. So you do the math, that must be 21 neutrons. And for electrons, like I said, if it's neutral, if it's electrically neutral, meaning no charge, then the protons equals the neutron. Protons equals the electrons. But in this case, it has a charge of 2 plus, meaning it has 2 more positive charges than negative, or in other words, it has 2 fewer electrons than protons, which is going to be 18. Notice, if we have 20 protons and 18 electrons, let me do one quick board calibration here while I explain. Anytime you have a positive ion, it's going to be giving away electrons or losing electrons. If you have a negative ion, it's going to be accepting or gaining electrons. So we have 18, that seems better, 18 electrons here. And generally, anytime you have an ion, that's going to match the number of electrons in one of the noble gases. This calcium ion has 18 electrons. Which other element has 18 total electrons? Argon. What do we know about argon? It's a noble gas. It's very stable. So as you can see, calcium tries to mimic argon's electron configuration to be more stable. Question 19. Categorize the following bond types as nonpolar covalent, polar covalent, or ionic. So we're going to use our reference sheet here. We see the electronegativity range right there. And we have electronegativities on the last sheet. So it's just a little bit of math and a little bit of categorization. So silicon is 1.8, phosphorus is 2.1. The difference is that right? 1.8 and 2.1. The difference is 0.3. Okay. And if you look at the front, a difference of 0.3 means this is going to be nonpolar covalent. Nonpolar covalent. HO. H is 2.1, O is 3.5. You know, for time's sake, let me run down the line and finish these out. Bromine is 2.8 and 2.8. Potassium is 0.8, oxygen's 3.5, phosphorus is 2.1, and chlorine is 3.0. Okay, so this will go faster now. So the HO bond, the difference here is 1.4. I'll kind of write the difference, 0.3 difference, 1.4 difference, and this is going to make this one polar covalent. Okay. And you can sometimes see a symbol written above it that looks like this. It points towards the more electronegative element, and you do a little plus sign above the more positive element. BR. So the difference here is 0, making this one nonpolar covalent. Yep. Any bond of the same atom is always going to be perfectly balanced and nonpolar covalent. Here we see a difference, what's that, 2.7, 3.5 minus 0.8, about 2.7. So clearly ionic, because my ionic range is anything 1.8 or above. And the last one, PCl, the difference here is 0.9, which is going to put us squarely in the polar covalent category. And if we want to use that symbol, we're going to point towards the more electronegative, which is the chlorine, and put that little line above that one. And so it's just using your reference sheets there. All right, question 20, scientists. So we're going to talk about the first 4 scientists in this question. So Dalton contributed the first concept of just the atom as a ball. Here's the Dalton model, just a ball. And we can say he proposed that atoms are indivisible spheres. No protons, no neutrons, no electrons. He didn't know about any of that, but he did propose the idea with some evidence of atoms being just a sphere. So we sometimes call this the billiard ball model or the hard sphere model. Thomson discovered the electron. Through the cathode ray tube experiment. Basically, he had a beam of cathode rays, which he was able to measure their charge. He noticed that it was negatively charged by using a magnet. He basically put the negative side of a magnet up to the beam and it repelled it. He put a positive side of the magnet up to the beam and it attracted it. So he knew the beam was negative. And then doing some advanced math, he was able to figure out the mass of the particles in the beam. And he found that it was 2,000 times lighter than what Dalton had proposed as the smallest atom, being hydrogen. So how could you have something negative that's 2,000 times smaller than an atom? Well, he invented the electron. So the Thomson model features electrons just kind of randomly throughout the atom like this. We call this the plum pudding model. I've heard it called the chocolate chip cookie model. And the idea here is the atom itself was neutral. So if it contains electrons, then the rest of the atom must have been positively charged. So sometimes we say it's like electrons moving around in like a sea of positive charge or like an ooze of positive charge. And that was a Thomson model. Rutherford discovered the nucleus. Essentially, what Rutherford did was he fired alpha particles in the gold foil experiment, which are very small, positively charged particles. Technically, they're helium nuclei. He fired these through gold atoms. And Rutherford didn't do this to disprove Thomson. You know, he had no problem with Thomson's model. This is what he believed atoms looked like. He was just working with like radioactivity or something along those lines. And he's firing these alpha particles through a gold atom, and he expected to see each of them have the tiniest bit of deflection, like not perfectly straight, but barely deflected. And why would that be? Because you're firing a positive particle through a positively charged ooze, right? It contained electrons, but the entire atom was positively charged. We expected a little bit of variation. What did he find? Oh, it was shocking. The famous quote, he said it was like firing a 15-inch artillery shell at a piece of tissue paper and having it bounce back at you. Most of the particles, something like 9,999 out of 10,000, went straight through with zero deflection at all. But every now and then, one of them was severely deflected, going off to the side, off this side, or even coming right back at the little sensor that was firing it. So major deflection. So to kind of sketch what that looks like, what do we got here? Let me go one more slide. Here was the gold foil experiment. Essentially, he's firing these alpha particles and major deflection like that. So what did he discover? Well, he realized that the positive charge must not be evenly distributed through the atom like Thomson thought. Instead, the positive charge must be extremely concentrated right in the middle of the atom. And that's what we now call the nucleus. So in the Rutherford model, we now have a teeny tiny positively charged nucleus in the middle of the atom. Now, he knew they still had electrons. Thomson wasn't wrong about that. So Rutherford wondered where the electrons could be, and he believed the electrons would essentially orbit the nucleus on rings. Maybe I should get rid of this outer ring here. That's kind of a better Rutherford model. It's going to look something like this. Okay. So your electrons kind of orbit on these rings, kind of like planets orbiting the sun there. Okay. I've been told by students this is the Jimmy Neutron symbol. By the way, Jimmy Neutron, James Chadwick. So that's your Rutherford model. The Bohr model was essentially looking at where the electrons were. So we have the positive charge in the middle. There's your nucleus. And what Bohr contributed was, we'll call them rings of electrons. Of electrons. Concentric circles. Concentric meaning same center, concentric circles. So he believed the electrons, and this was his work with light, looking through like atomic spectra. He realized that electrons exist not on these orbits, kind of like Rutherford said, but on these discrete, separate, he called them energy levels or shells, and that electrons could jump up and down between them. And when they jump up, they absorb a little bit of energy. When they jump down, they release energy, and that released energy is what we perceive as light. So this is why certain elements will give off different colors when they're, we literally use the word excited. When you excite an atom or excite an electron, it'll jump up, it'll jump down, it'll release energy, and we can perceive that in a color. So the main thing is the rings of electrons here. I didn't touch on the other scientists, but you should have a very basic understanding of them too. Schrodinger was one of the main contributors to the quantum mechanical model. Think of that as the three-dimensional model, the one where instead of rings like this, it's more like three-dimensional lobes. And when you were looking up for your project, you may have seen these weird like bow tie looking shapes. That was Schrodinger's quantum mechanical model. Heisenberg was all about uncertainty. Probably saw that uncertainty principle. The idea is you can't know exactly where an electron is and how fast it's moving, that sort of thing. The example I use for that is a fan. If you're looking at a fan when it's off, you can tell how many blades there are, right? You can see 1, 2, 3, 4, 5, and you can tell where they are, right? But once you turn the fan on, they're moving so fast that you know the electrons are in, you know the fan blades are in a general vicinity, but you couldn't ever tell me exactly where they are or how fast they're moving. That's the idea behind the uncertainty principle. And lastly was James Chadwick, who invented the neutron, which was very important because that paved the way to the creation of the atomic bomb and later of atomic energy. Neutrons are essentially the trigger we use to set off an atomic bomb or to power like a nuclear power plant. Okay, so those are your scientists. Number 21. All right, this is the final problem, and this will be a long one. Obviously, I'm dealing with a lot of structures here. So for each of the following molecules, draw the Lewis structure, identify the VSEPR shape, and identify whether it's a polar or non-polar molecule. So let's start with silicon tetrabromide, which is going to be SiBr4. Okay, first step, we make a skeleton, what I call a skeleton model, where we just put the lone element in the middle, surrounded by 4 elements on the outside, in this case. Okay. Now we put our dots around each element until every element has the octet rule satisfied. What's the one element that's never going to follow the octet rule? Hydrogen. Okay, there are a couple other examples as well as exceptions, like you see here, boron violates it. All right, so that's our skeleton model. Now that might be correct, that might not be correct. Here's how we confirm. We check 2 numbers. We add up the number of electrons you see in this model. Now the lines are single bonds, which are 2 electrons each. The dots are electrons, which are 1 electron each. So looking around this, I'm going to count around each bromine, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So I get a total of 32. Write that number down, 32. The next thing I do is I look on my periodic table, and I'm going to look up the valence electrons in each of these elements, or atoms, I should say. So from the periodic table, groups 1 through 18 can also be labeled 1A, 2A, skip, 3A, 4A, 5A, 6A, 7A, 8A. And by that measurement, the number of valence electrons is like the 1, the 2, 3, 4, 5, 6, 7, 8. So silicon is in group 4A, that has 4 valence electrons. Bromine is in group 7A, 7 valence electrons. So there are 4 bromines, 7 times 4 is 28, plus silicon's 4 is 32. Hey, look, the numbers match, we're good. So that's our Lewis structure for silicon tetrabromide. Now we need a Vesper shape. So we don't need to have this memorized. You can refer to the front cover here. Now, some of the terms we need here. We have total electron domains, or areas to find electrons. An electron domain is either a single bond or a double bond or a triple bond or a lone pair. They all count as the same. And we're only looking at the central atom here. We're not looking at any of these VRs. We're just looking at the central atom when it comes to Vesper shape. So the central atom is that silicon. How many electron domains do you see? 4. There are 4 single bonds, no double bonds, no triple bonds, no lone pairs. So we have 4 electron domains. Now, of those 4, how many of them are bonding pairs? All 4 of them. A bonding pair means either a single bond or a double bond or a triple bond. So we have 4 bonding pairs. How many lone pairs on the silicon? 0. So we check our chart for 4 electron domains, 4 bonding pairs, 0 non-bonding pairs, and the shape we can see here is a tetrahedral shape. So you might think of this as like a cross-shaped molecule. That's not true. You're not thinking 3-dimensionally. In reality, it's going to look more like this. I'll do my best to kind of draw this. Like 1 bromine here, 1 bromine kind of sticks out like this, 1 bromine is like that, and the last one comes up. So it's sort of like a tripod looking thing on the bottom with 1 sticking up. And sometimes if you go into higher levels of chemistry, generally one of these is going to come out of the board towards you. We symbolize that with like a darkened wedge. And another one's going to be going into the board behind you. We show like lines like this. So you might recognize that notation. Or if you're Googling things like this, you might see that notation. That's how you try to show 3 dimensions on a piece of paper. Okay, so again, our Vesper shape for this one is tetrahedral. And the last question we ask is identify whether it's a polar or nonpolar molecule. Now remember we said polar covalent versus nonpolar covalent versus ionic? This has nothing to do with that. Nothing to do with that. It literally just comes down to, does the central atom have lone pairs of electrons on it or not? That's it. If the central atom has lone pairs of electrons, it's going to be a polar molecule. If the central atom has no lone pairs of electrons, it's going to be a nonpolar molecule, assuming all the branches are the same element. So looking at our list here, linear, no lone pairs, that's going to be a nonpolar molecule, assuming the 2 branches are the same. Trigonal planar, no lone pairs, nonpolar molecule, assuming all the branches are the same. Bent, lone pairs, polar. Even if all 3 of these are the same, by the way, that's going to be polar, the same element. Tetrahedral, no lone pairs, nonpolar molecule, as long as all the branches are the same. Trigonal pyramidal, lone pairs on the central atom, polar. Bent, 2 lone pairs on the central atom, polar. It's as simple as that. If you see those dots on this reference sheet, it's going to be polar molecule guaranteed. If you don't see dots, as long as the branches are all the same, nonpolar molecule. So with this one in mind, we see a tetrahedral shape. We see no dots, no lone pairs on the silicon. This is going to be a non-polar molecule because all 4 of the branches are bromine. So they're essentially tugging equally in either direction. You know, if I had 4 people, if I had like ropes attached to me and 4 people were standing perfectly across from me in all 4 directions and pulled evenly, would I move? No, I would have an even distribution of pull going on. Weird example, but it works the same with electrons. If you have 4 bromines tugging on your electrons, you're going to be evenly distributed with those electrons, and there's going to be a nonpolar molecule. All right. Next one, we'll go a little quicker now. Let's go across. Carbon monoxide. So CO. We start with our dots around all of these elements. And now we check if this is correct. So I'm counting 2, 4, 6, 8, 10, 12, 14 electrons. That's my total. I now check my periodic table. Carbon has 4, oxygen has 6, 6 and 4 is 10. I can tell I have 4 too many. Now, if you're quick with these, you might recognize you're going to need a triple bond right away. A double bond gets rid of 2, a triple bond gets rid of 4. But let's go stepwise. Let's first make a multiple bond by getting rid of 2 of these and 2 of these and making a double bond here. Okay, so just once again, to turn a single bond into a double bond, you remove 2 electrons from each of 2 neighboring electrons, neighboring atoms. So I do that, and that should bring us down to 12. 2, 4, 6, 8, 10, 12. Okay, we're not done yet, but we're getting closer. So now I'm going to do the same thing again. I'm going to remove a second pair of electrons, create a triple bond, and now we have 2, 4, 6, 8, 10. We have what we need, and that's our Lewis structure. And as you can see, the carbon satisfies the octet rule. The oxygen satisfies the octet rule because they're each experiencing 6 electrons in that triple bond, and they each have 1 lone pair. Okay. Lewis structures, Vesper shape. Okay. Now this one actually doesn't really fit any of these evenly because we really don't have a central atom here. But this would generally be considered a linear molecule because it's 2 of them, and this is going to be polar. Okay, it doesn't quite fit what we have here. So I actually wouldn't expect carbon monoxide as your example there. But because we have different branches here, the oxygen being the more electronegative is going to kind of pull those shared electrons closer to it, creating a negative charge on its side. So linear and polar. All right. Let me make a few. I think I'm going to do 1 slide for each of these. So I got to clone some slides here. Give me a sec. Clone. 1, 2, 3, 4, 5. 1 more. Okay. Next, ozone, O3. All right, so we line up the O's like this. Okay, 1 in the middle, obviously. We put dots around these. Forget the 1 in the middle. The dots serve to satisfy the octet rule. So they each now have 8 electrons around them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right, now we look at our periodic table. So oxygen has 6 valence electrons, so 3 oxygens gives us 18 valence electrons. As you can see, the numbers do not match, so we need to make a double bond. So let's take 2 off this one, 2 off that one, and give ourselves a double bond right there. And now we're down to 18 and 18, so we're good. Okay. So this, looking at our Lewis structure looks good. Our Vesper shape, let's count our electron domains. 1, 2, 3. I see a double bond, which counts as 1. I see a single bond, and I see a lone pair. That's 3 electron domains. How many of those electron domains are bonding pairs? 2 of them. And maybe I shouldn't use the word pairs because the double bond isn't a pair, but we have 2 bonds, a double bond and a single bond, and we have 1 lone pair. So it's 2 bonding regions and 1 non-bonding region. So looking at your chart, where do we have 3 electron domains, 2 of which are bonding and 1 is non-bonding? The answer is bent. And this makes sense because it's not really going to arrange itself like this. That central atom, the lone pair on the top, is going to kind of bend those arms down. Like if I represent this ozone, I'm the middle and the 2 O's are my arms. Well, if I have 2 electrons on the top of my head like that central oxygen does, it's going to bend those 2 arms down. So it's going to have that bent shape like this. And because it's bent, it's polar. How can it be polar if it's three of the same elements? Three of the same, elements, three atoms of the same element. Well, it's because it doesn't come down to the difference in electronegativity, which is 0 between each of these atoms. It only comes down to, does the central atom have a lone pair or does it not? And because this has a lone pair, it's a polar molecule. Simple as that. All right, next one, ammonia Nh3. So the central atom is the N. We're going to stick 3 H's around it. Generally, when you have 3, you go left, right, and up. Let's add our lone pairs. Now remember, H does not get any lone pairs. Hydrogen can only hold 2 electrons, and by having that line, which is 2 electrons, it's done. But what about that N in the middle, the nitrogen? Yes, that needs 2 electrons because right now it only has 2, 4, 6. So that's our skeleton structure. Let's check if this is correct. So I count 2, 4, 6, 8 around it. Nitrogen has 5 valence electrons. Hydrogen has 1. So 3 hydrogens is 3. 5 and 3 is 8. Hey, we're good. That's the Lewis structure. All right, for a Vesper shape, we're just going to count the electron domains. There are 4 of them. There are 3 bonding pairs or 3 bonding regions and 1 non-bonding. So what do we get? 4, 3, 1, trigonal pyramidal. You might think this would look like a triangle, like an N in the middle and then 3 H's perfectly sticking out in perfectly opposite directions. So like bond angles of 120, I guess. But that lone pair causes them to kind of bend down. The lone pair is going to be on top. So it's going to end up looking more like this. If I can draw this as 3-dimensionally as I am able to. That's not a very good drawing, but try to picture those H's as like a little tripod with the end sticking out of the top. So that's going to be a trigonal plate pyramidal molecule. And when it comes to polarity, it's very simple. Do you see lone pairs of electrons on the central atom? Yes, therefore it's polar. Okay, 4 down, 4 to go. Oxygen difluoride. So the oxygen is in the middle. The lone element always is. I put an F on one side and F on the other side. Lone pairs around the fluorines. Lone pairs around the oxygen. Okay, let's count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons in my model, my Lewis structure. And now I'm going to add up the elements from the periodic table. Oxygen is 6. 2 fluorines is 7 and 7, which is 14. 6 and 14 is 20. And we're good again. That's the Lewis structure. Now, at first glance, you might say that's going to be linear, right? An oxygen in the middle with 2 fluorines that are going to stick out perfectly. It'd be like if my arms were fluorines, they'd stick out. But you're not thinking 3-dimensionally, because what else does that oxygen have? It has 2 lone pairs. And if you're thinking, yeah, the oxygens go left and right, the lone pairs go up and down. You're still not thinking 3-dimensionally. 3-dimensionally, a tetrahedral shape is the way 4 electron domains are going to arrange themselves. But since 2 of them are bonding regions and 2 of them are non-bonding regions, we're going to end up with a bent shape. So we had a bent one before with 1 lone pair. We're also going to see a bent one with 2 lone pairs. So the way this will end up looking is something like this, with an oxygen, a fluorine, there's your other fluorine, and then like a lone pair here and like a lone pair down there. Not the best drawing. In fact, I'm going to erase that. So our structure is bent. And when it comes to polarity, you ask yourself one question. Does the central atom have 1 or more lone pairs? Yes, it does. It has 2 lone pairs. This makes it full. Carbon dioxide. CO2. So the carbon goes in the middle, oxygen, oxygen. All right, lone pairs go all around the oxygen, all around the carbon, all around the oxygen. And now we check if this is right. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons in my CO2. Now carbon has 4 valence electrons, oxygen has 6. 6 and 6 is 12. 4 plus 12 is 16. So we do not match, so we need to start playing around with this. Well, a double bond will cut you down by 2. So let's do that first. Remove 2 from that and 2 from that, which gives us, calibration's starting to go. I can feel it. Carbon. All right, so there's our double bond. That brings us down to 18. Now we have one more to do. Now, in theory, you could put a triple bond on one side, but it's never going to truly balance that way. If it's like if you're bench pressing 100 pounds, you're not going to do 75 pounds on the left and 25 on the right. No, it's going to balance out. So on the right side, we're going to make a double bond as well. So we're going to take these away and make a nice double bond there. That brings us down to 16, and that is our Lewis structure. So notice we have a carbon in the middle, 2 double bonded oxygens on the side. Okay. What's this shape going to be? Well, how many electron domains do you see on the central atom? 2, because remember, a double bond counts as 1 electron domain. So I'm seeing a double bond and a double bond. When those are sticking out, they're going to go in perfectly opposite directions. It'd be like if my 2 arms hate one another, where are they going to go? Perfectly straight across. This makes this a linear molecule. Do we see any lone pairs on the central carbon? No. As long as the 2 branches are the same, I have O and O, this is going to be a nonpolar molecule. All right, phosphorus triiodide, Pi3. So the P goes in the middle, I. Lone pairs around each of these I's. Make sure you get a lone pair on the P as well. That phosphorus only had 6, now it gets 8. All right, let's see if this is correct. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. All right, 26 electrons. And now we check the periodic table. So 1 phosphorus is 5. 3 iodines is 7, 7, 7. So that's 21. 5 and 21, 26. We're good. So that's our Lewis structure. All right, for Vesper, we're going to check the bonding regions, or I should say we're going to check the electron domains first. I'm seeing 3 single bonds and a lone pair. That's 4 electron domains. Of that, 3 are bonding, 1 is non-bonding. This is going to end up being a trigonal pyramidal shape. Trigonal pyramidal. Essentially, that lone pair is going to bend those 3 hydrogens down. So you're going to see them down like that. Does the central atom have a lone pair? Yes, it does. That's polar. Simple as that. Right? Even though the Pi difference in electronegativity, it's 0.4, but that doesn't matter at all. I was going to say, even if the difference is less than that, it does not matter. I mean, we literally saw ozone, which was OOO, ended up being a polar molecule, not because of the difference in electronegativity. That doesn't matter. It's all about the whether the central atom has lone pairs. All right, last one. And as you can see, we have an exception here. Boron trifluoride is going to be BF3, but boron violates the octet rule, only needing 6 valence electrons. So we're going to put a boron in the middle. We're going to put 3 Fs around it. And we're going to put our dots. Each of the fluorine gets 6 electrons. And normally we would stick 2 electrons on the bottom of the boron. But as you can see by the example, due to factors beyond the complexity of an intro to chem course, the boron is satisfied with 6. So we're going to leave it just like that. Let's check if this is correct. So boron has 3 valence electrons, much like aluminum below it. 3 fluorines is 777. That's 24. I guess I'm going out of order here. So 24 is the BF3. Now let's add up my elements, my electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So notice we're good. So BF3 looks like that. For our shape, how many electron domains do you see? 3. Single bond, single bond, single bond, meaning there are 3 bonding regions and 0 non-bonding regions. So this makes it trigonal planar. This is going to be the boron in the middle, and there are 3 fluorines are going to perfectly spread out 120 degrees apart. Trigonal planar. You know, like a triangle on a flat plane, as opposed to trigonal pyramidal, which is a triangle on a pyramid. Okay, last question is for our electronegativity difference. Polarity, which is not electronegativity difference. In fact, boron is 2.0. Fluorine is 4.0. That's an absurd difference in electronegativity. That brings you into the ionic range. However, despite that, this is going to be a non-polar molecule. Why? Because the boron in the middle has no lone pairs. So the fluorines are evenly tugging it in perfectly canceling directions, and there's no charge there. All right, so that does it for this study guide. Well, best of luck, everyone. Make sure you study hard, go to extra help sessions, and be proud of yourself. You made it through a tough year of chemistry, and good luck with your test coming up.